Okay, just finishing off this example, we know that PM and QN intersect when mu equals lambda equals half. Okay, and when we substitute either one into R1 or R2, we'll work out the point of intersection. So let's just go R1 here, we'll sub in lambda equals half. You'll get 0 plus half times 1, negative 2 plus half times 3. The y component is going to be 0 plus half h. Okay, so that would be vector OX, and we want it written, find the position vector, so I can leave it in vector form. Let's just simplify this. That'll be 1 half, that's negative a half, and that's h on 2. Okay. All right. Next page 8. So this bit's on parallel, perpendicular, and skewed lines. One thing we need to be able to do is to decipher whether lines are parallel, perpendicular, or skewed. So what does it mean for two lines to be parallel or perpendicular? The key thing is it's all got to do with their direction vectors if they're parallel or perpendicular. Okay, two lines will be parallel if their direction vectors are parallel. So the direction vectors are scalar multiples of each other. Okay, so here's an example where I've got two lines, and if you look at the direction vectors, we can take the ratio of the x components, the ratio of the y's, and the ratio of the z's for the two direction vectors, and we see we get a common ratio of negative a half. Okay, so therefore they'll be parallel. The other way of doing it is taking one of the vectors, so for example this vector here, and factorizing and getting the other vector. If you take out a negative 2 here, you'll get 3, negative 2, and that'll be positive 4. So we've got that one of the direction vectors is negative 2 times the other direction vector. It's a scalar multiple, therefore parallel. So that's the other method of showing parallel. Okay. And two lines are perpendicular if their direction vectors dot product to give 0. If the direction vectors are perpendicular. And two lines can be perpendicular if they touch or if they don't touch. They don't need to touch to be perpendicular. So in 3D, lines can be parallel. That's horrible, but you get the idea. Not parallel and touching, intersecting. Or you could have skew lines, which is not parallel and not intersecting. So it could look something like a line, and you can draw, let's say, a line underneath by drawing that kind of effect where you let the line go. Looks like it's underneath. So skew lines are lines that are not parallel and do not intersect. Okay, so this is what we usually do. This is kind of the order that I'd suggest a recipe. Test if they're parallel first, then test if they intersect. I'd test parallel first because that's the easiest test. Then test if they intersect. If the answer is no to both of the above, the line is skewed. Okay. So let's determine whether these lines are parallel, intersecting, perpendicular, or skewed. So let's test for parallel first. Okay. So I'm going to write down their direction vectors. So look at the coefficients of the parameter. 2, negative 1, and 3. I'm going to call that B1. And over here, the other line, B2, it's going to be the coefficients of the parameter S, 4, negative 2, and 5. Okay, I can take ratios of the x components, y components, and z components and see if they're equal. So 2 over 4 does equal to negative 1 over negative 2, that's a half, but that does not equal to 3 over 5. So therefore, L1, lines are not parallel. Okay. Next, we're going to test if they intersect. Okay, so let's equate the parametric equations for x, y, and z. So for x, that'll be 3 plus 2t equals to 1 plus 4s. For y, that'll be 4 minus t is equal to 3 minus 2s. For z, that'll be 1 plus 3t equals to 4 plus 5s. So it's equation 1, 2, and 3. Okay, 2 equations, 3 unknowns. We pick 2 equations and solve simultaneously. I think probably the easiest 2 to solve simultaneously, maybe 1 and 2. Okay, I'm going to take equation 2 and times by 2, and I'm thinking about eliminating t here. Okay, so adding that with equation 1, so I'll write equation 1 underneath. Oh, something interesting happens when I add that. Over here we get 11, over here we get 7. 11 equals 7. Well, that's not true. So therefore the first 2 you can't solve simultaneously together. So therefore lines do not intersect. Don't intersect. Okay. You could have picked a different pair. You might have got an answer with 2 and 3, but then you would sub into 1. It wouldn't work. All right. So anyway, we get something that doesn't work. It isn't consistent among the 3 equations for s and t. So therefore, they don't intersect. So if they don't intersect and they're not parallel, the conclusion is therefore L1 and L2 are skew lines, as they are not parallel and do not intersect. Do not intersect. Each other. All right, next. Last question we'll do in this video, and then you'll be up to date to where we started. Prove the 2 lines defined by those 2 vector equations are perpendicular. Remember, key thing to be perpendicular, the direction vectors must dot to give 0. So that's what I'm required to prove. So let's go. B1 dot B2 equals. So the first direction vector is -2, 4, 6. The second direction vector is 5, 4, 1. Let's dot product that. We get -10. Oh, careful. There's a -1 there. So it's going to be -10 plus 4 times 4 is 16, and then minus 6. And when we do that, we get 0. So because the dot product of the 2 direction vectors is 0, therefore the 2 lines are perpendicular. The 2 lines are perpendicular. All right, and there you go.